So today we're going to talk about review for the midterm. We're actually going to talk about a couple things. I will do a quick Unix tip of the day. And then I have a couple comments on TAs. Actually, I'll go through that first. Then we'll do the midterm review. This is your chance to ask any kind of questions you have. We'll do I will kind of review all the topics that we talk about. I'll kind of give you pointers as far as what things I think are important. And then we'll go over some practice questions. I'm not going to give you the answers necessarily, but we'll go over some practice questions that the types of things you'll see on the exam. I don't think you'll see any specific ones, but you'll see similar types of questions. So that'll be good. Comments on the TA. So I totally forgot to mention this last week, and I didn't want the person who sent me anonymous feedback to think that I had ignored the comment. But when you send me anonymous feedback, you can, by the way, set it up so that I can email you back and you remain anonymous. So if you happen to want to reply, maybe this was just a rant, but it was somebody posted that a TA actually didn't show up for office hours one of the nights last week, and they were saying, well, you know, it'd be nice if the TAs showed up. And I'm like, yeah, of course. And I wanted to know. We actually polled all the TAs or told the TAs this and said, start showing up. And if you're not going to show up, at the very least, post something on Piazza. But even better, find a replacement. And we figured out who it was. The person actually emailed back and said, oh, I'm so sorry I missed. So we fired him. But no, we didn't fire him. But we could have. I mean, I say that in jest. We did not fire him. But I think the point is that it's bad news if somebody's skipping their TA office hours. So if you go to office hours and there should be TAs there and no one is there, and by no one is there, that could mean a couple different things. It could mean they skipped it. It could mean that they're in another room and they just hadn't been walking around to different labs. And in that case, you might want to just ask at some other labs, are there any 15 TAs around here, just to make sure. Or it could be some other anomaly that we don't know. But please let me know. And it can be anonymous if you want. If you don't want to call somebody out, I don't mind. But please let me know so that we can track these down. Because we're paying TAs and they should be showing up for these things. It's a real job. So I don't want you guys to suffer like when you go and expect a TA to be there. All right. So anyway, we have taken care of that issue from last week, and hopefully it won't happen again. But if it does, please email me. Questions on that? OK. All right. Let's do the Unix tip of the day real quick. So let's say that you are in it's Tuesday night, and it's like midnight, and you've been studying, and you're sick of studying. And you want to go find out if Chris put up the midterm online so you can just like look at all the midterm questions, right? There's a find function in Unix commands. Now, unluckily for you, I actually have permissions set on my directory so that you hopefully cannot do what I'm about to show you. But let's say you wanted to find a file in some folder, and it happened to be called midterm or something, right? Maybe it's your own midterm study, and you forget where you put it. If you type the following command, find, and then you can type dot, which means the current directory you are in. You could put any directory. You could put slash, which would mean the home directory of everybody, and it would probably never finish because it would have to look through all the files in the whole server. And it wouldn't find most of them because most people's permissions are set, so it couldn't do that. But if you type find and then dot and then dash iname, right, which stands for, it says by name, but don't worry about the uppercase, lowercase of the name. And then if you put in quotes something like star midterm star, which means find everything where midterm falls somewhere in the word, right? It might actually find something, right? So like there's my midterm folder, right? And there's the text file that's in the midterm, right? And then if you were lucky and I didn't have my permissions set, you could go to midterm, right? Let's see, midterm 2014 spring, and then you could type the file out, and then it would say, haha, as you think, right? But anyway, if you want to find files, you can do that. You can also find files by the file, whether it's a file or not. So if you let's see, if I went back 2 directories again and did the same thing, find dash iname it. So let's see, find dash type, I think it's type F. Yeah, there we go. It would just find you can't see it really. It would just find the file, not the folder. You could also find just directories, type equals D for directory. Oops, type D. and then it would just find the directories that happen to have those search terms. So it's a nice way to search through all your files if you don't remember where you put them. And as your folders get bigger and bigger, you might want to do that. And for, if you might want to, for the midterm, study for something and be like, hey, during a lab, I remember we talked about, pushing, like using a stack to do a traversal of a tree. And if you type stack, do this thing and type stack, right? It should hopefully find. Let's see, this one would be directories. Let's find anything. I don't know, if you happen to have something, there we go. There happened to be a stack.cpp, and go look at that. So anyway, it's a good way to find your files if you need to search for them. OK, questions on that? Yeah? Is
there an argument that searches for text within a file?
There is. There's the grep, which I think we may have covered somewhat before. But grep, like let's say I happen to know day 9. Actually, you could do a very similar type of search, grep-r, which is for recursive, to search through all the directories. And then if you type, let's see, stack and then star for all folders, it'll start searching through and it'll tell it, it's listing out every file it finds the word stack somewhere in it. So that's kind of cool too. Yeah. I thought we did grep. Maybe we didn't. Yeah, maybe we did. But anyway, that's how you'd search through those ones. Questions on that? OK. All right. That was a quick, easy, quick and dirty tip of the day. OK. So the midterm review. So I'm going to go through a couple study tips. I've already gone over some of this before. But you're definitely allowed one page back and front, handwritten set of notes. I probably won't stomp my foot, but there's going to be some things in here that I suggest you write down on there. Like, for instance, the different types of the different types of analysis, big O analysis or something. You might want to write down all the, kind of what the basic idea is for those, for instance. You can certainly write down how to rotate an AVL tree or whatever you want. I mean, honestly, I think the key is that you study from it and get the benefit from that. Obviously, there's slides. There's some notes online on the lectures webpage. Lots of code samples. I suggest reviewing the code samples, particularly from the two big assignments we've had, homework 2 and homework 3. Go back and review the code that you had to write, because I will probably ask some questions based on that. Now, you won't have to know. You won't have to like remember, oh, that was the variable, blah, blah, blah. It should have enough information in there in the setup for the problem that I give you that you'll be able to do that. If not, just make it up and it'll be fine. I mean, if you're talking about the day list and you forget it was called the day list, well, write something, whatever you write, point to and say that's the list of days or whatever. So don't worry about that. But go through the code to kind of refresh your memory about that. Obviously, the videos, if you want to spend the time to look at the videos, and if you missed any of the classes or videos, now's the time to, well, probably 2 weeks ago was the time, but go look at the go look at the videos and actually watch them, because I think a lot of the stuff we covered in class is fair game on the, well, all of it's fair game on the midterm, except for the obfuscated C. I don't think I'll make you. Maybe a bonus. I don't know. We'll see. Anyway, homework assignments. Review the labs. At least go and refresh your memory about what we did in the labs. I already mentioned the lab that we did, the stack, using the stack to do the lab traversal. You might want to go kind of refresh your memory on how that whole process works, just because I could ask a question and say, how would I use a stack to do blah, 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 right? So those are the big items. Yes?
Do we have labs this week?
We do have labs this week. This week's lab is on debugging with a debugger. So you actually get to use DDD. Those who did it already, did it come out all right? Yeah. It was a little tricky. There's a whole bunch of steps you need to follow, and learning a debugger has a big learning curve in general. But it's yeah, Nanbi's like, but once you get a hang of it, you will find it very useful for future projects in here, and certainly future projects if you take, say, Comp 40 or whatever. You'll use debuggers all the time because it just makes your life a lot easier. So anyway, we'll learn that. So there are labs this week. You won't have to know debugging with a debugger on the midterm. I'll put it that way. OK, questions? Yeah?
Should we study from the textbook?
No, don't worry about the textbook. I mean, the only thing you could, if what we've talked about so far isn't enough information, like you still don't get what a binary search tree really is, yeah, go to the textbook and look it up. I don't really love the textbook, to tell you the truth. I've said that before. But there won't be any specific questions on anything the textbook covers that's outside what we covered in class. Okay. Other questions on that? Other things? And by the way, keep answering questions. I mean, I have a full set of stuff today, but there is some buffer room to answer lots of these kinds of questions on this stuff. OK, so here's the types of problems I could ask you. OK, obviously short answer type questions. And those are going to be the ones that I don't want you to write code about, but I want you to demonstrate to me that you understand what, like for instance, where's a linked list better than a dynamic array? Right? Where's a, why might I want to use a tree instead of a dynamic array? Those kind of thought questions that tell me that you understand what the data structures are and what the and what we've been talking about from a broader scale. I will ask you to find some bugs. I think you're probably pretty good at that. Don't spend too much time on those problems. Like people spend way too much time trying to find minuscule little bugs. I will not ask you bugs that are. I will not highlight bugs that are like there's a semicolon missing or there's something else like that. C++ syntax is not really the idea here. The idea is more the logic of the program. Did you have the right number of iterations through the loop? Is your for I equals or I is less than whatever number the right one? That sort of thing. Yeah.
For finding the bugs, will you tell us how many bugs are in a segment of code?
I might not tell you how many bugs, but I might say find. I might say find 2 bugs in this program, or at least 2 bugs, or something like that. Yeah. That one shouldn't. Yeah. I don't want you to spend and I won't give you one where find the bugs and there are no bugs. Don't worry about that. There will be a bug or 2. All right. You have to explain what some code does, possibly. Definitely have to determine big O bounds. We'll talk more about that when we talk about asymptotic notation in a little bit. And then you'll have to do a little bit of explaining C++. So there is a little C++ on there in terms of kind of we talked about 4 big things that I would say you hadn't seen in Comp 11 or any other, or certainly Comp 50. But for instance, destructors, the copy constructor, the operator overload constructor or operator overload function, reference variables, like what's a reference variable versus a pointer, stuff like that. And I'm not going to ask too much detail, but I want you to just demonstrate that you know the basics of why these things are needed and when we might use them. OK? Questions on those? All right. All right. So here's the topics that we've covered so far. It's hard to believe we covered this many topics. It seems, we've only been here, 14 days or something, and 14 lectures or whatever. We did some C++. Arrays, you all are pretty good at arrays, I hope. Difference between static and dynamic arrays. Linked lists. There are a lot of linked structures, right? Not just linked lists. Trees are linked structures. Priority queues can be linked structures. Some of the other we talked about lots of different types of linked structures, but in particular, singly and doubly linked lists. We had that whole homework assignment on the singly linked lists. Well, the one that you needed to do the event and day list for. We talked about recursion. I'll get into the details about some recursion and what you have to know about that. There will be maybe a minor code writing recursion thing, but you will not have to write long sections of code particularly for the recursion one. I'm not going to make you write some arcane recursion problem. It'll be something just to kind of demonstrate that you know how it works, and then you can think through a kind of a small problem. Stacks and queues. We're gonna go over a little more detail about that, about the details there that we've already covered. But you should know the differences. You should be able to compare them. You should be able to say when you would want to use one over the other, for instance. Which one would we use for a level order traversal? We did it in the lab 5, 4. Which one? For the level order traversal. That was the one. You need to know things like this too, right? What's a level order traversal, right? If you have a tree, and it's like this, right? Level order is going this way, then this one, then this one, then this one, then this one, this one, this one, this one, this one, right? And I don't think you can do it with a stack. How about a queue? Yeah, you'd have to remember we put the things in the queue, and then you'd put this one in the queue, then you'd pop it off the queue, or you'd dequeue it, then you'd put its children in, and you'd print it, then you put its children in, and then each one of these you'd pop individually and put its children in, right? We did that with the queue. So you need to know stuff like that. All right, this whole side is about trees. It looks like we covered more on trees than everything else, but there was a fair amount on trees. We talked about kind of the general idea of trees, what they are. They're node-based structures. They branch out, so on. Binary trees in particular, BSTs for binary search trees. AVL trees, and then, let's see, this should not be under trees. I don't know why it is. Asymptotic big O notation. We have to, that kind of goes through the whole course, really. We should be able to back up and go back and look at some of the dynamic arrays and say, what's the big O notation, which we've been doing in class. Then we talked about tries, and then finally we ended up with priority queues. Okay? Certain ones of these, like priority queues, well, some of these ones, like AVL trees, I'm certainly not going to make you try to write the code to do inserting into an AVL tree, right? This is not, we don't have time on the test, and it doesn't seem worth it. But you might have to draw pictures of these things. What happens when we insert this node or delete this node? What happens to the tree structure? And you might have to draw the picture. Okay? Any other topics that I missed? I think I covered all of them, the big ones anyway. Yeah?
You're talking about don't worry about the syntax for that, how to write that code out.
Yeah.
A similar thing apply to stacks and queues?
Yeah, good question. So stacks and queues, so the AVL trees was a particularly difficult one to code. Stacks and queues I don't think are that hard to code. I mean, you need to, if you're implementing a stack with an array, right, well, the last element's going to be the one you pop off, so you should be able to reason through that. So no, it doesn't apply to some of the other ones. Yeah, good question. Anything else on those? OK. All right, let's go through some of the details of this stuff, kind of refresh our memory and go through some practice problems as well. So for C++, we did talk about the big three, right? Destructors, copy constructors, the operator overload, and reference types. I already mentioned all that. We also talked about this idea of dynamic versus automatic memory. Okay? If I type something like this, or I say something like this, day d semicolon, is that an automatic memory declaration or a dynamic memory declaration? Which one? Yeah, if we don't know what that means, that's kind of a big deal. But in this case, this is an automatic because you don't use the new keyword. OK, that's really the key to figuring this out. If instead I had said day star d equals new day, right, something like that, well then, now you know, OK, I'm using this new keyword. This is a pointer. That's what the new gives me. And this memory is something that I'll have to take care of later. Like I'll have to delete it later, but it actually remains for the whole rest of my program until I delete it. This one, what is the scope of this? Either the function or wherever you declare it. If you declare it in your function, it's going to go away at the end of the function. And if you don't copy the data out of this to some other permanent structure, it will go away. And then you'll end up with segfaults later when you try to access it. Things like that. Okay? And we saw a lot of that with I think it was the return new day or whatever. People were trying to do this. Return, or I guess it was just return new day in the homework 3. And they were getting segfaults all over the place. Well, you had created new day up here like this, and then tried to return it. And when you use it later, it's gone already. So, Allison, you had a question.
Well, when you say day,
yeah.
declaring a variable that is type day, you're not actually like.
That's what you'd think. In this case, this is actually it's a feature of C++ that when you do this, it calls the default constructor on this. Yeah, for integers and other primitive types, yes, that's the case. But for classes, this actually calls the destructor or the constructor and makes it for you. Yeah, yeah, good question. All right, but anyway, just the kind of the broad idea of that. Okay. And then we did talk about asserts, right? I mean, we talked about how to use asserts and maybe when to use them. And I guess my big question about that is, do we use asserts primarily for debugging or for, what's the word I'm looking for error handling? What do you think? Yeah, a lot of people think it's error handling. But how many times when you're using Microsoft Word does it crash and it says assert failed? Right? I've seen it like once in my life from like a commercial program, right? And you generally use asserts to do debugging kind of things, not error catching. Now, we've used them kind of to catch some errors. But more, you use it when you have a situation where there should be no way that a certain value gets through to your program. That's when you say, I gotta fail. Now, you probably should catch that earlier if you're writing the rest of the program. That's how the asserts work. Okay?
When did
Yeah.
you use these, or I don't know the-
We've used them. Well, we used them in the first homework assignment. We said we have to assert that that like the rectangle parameters are not less than 0. Right? Remember that, greater than 0. We've also used them in some other places where, like, if you check to see if a stack is, let's see, if you try to pop something off a stack that happens to be empty, well, that should cause a program failure, right? Because you shouldn't be able to, you should check to see if the stack is empty using isEmpty before you call pop. That's just the way it goes, or top, for instance. So those are the kinds of things. I will not expect you to write asserts into your code that you write for the midterm, but I might ask you a question on what's an assert, why do we use them? Good? Question, Mommy?
So asserts aren't really essential to our functions. So you just write assert statements.
Yeah, asserts, yeah, I mean, asserts are not essential. They do help you debug, and they also kind of make it so that your program won't go off on some weird value. Like, remember the first homework assignment where we used, some people's programs were printing out like negative widths for perimeter, or negative perimeters and all that kind of stuff because they allowed negative widths and lengths? Well, you should probably avoid that, right? You shouldn't have something that's physically impossible to be able to come out of your program. So that's when we'd use them. It's those kind of situations. But you're right, it won't make your, well, it could make your program fail if you didn't have the assert because you allowed bad data to get in there, but it won't affect the proper running of your program, certainly. Yeah, question? Yeah, it's to try to keep the bad data out of your function is really what the big idea is. Yeah, question?
I'm still not entirely clear on copy constructors and operators.
OK, good question. What do we use copy constructors and operator equal overload for? OK. Let me go back one step. When do we use a destructor? In fact, I think that's the sample question here is when do we use a destructor? And when do we not need to use a destructor? Can you answer that part?
Usually don't use them at the end. Use them at the end to delete dynamic.
Yeah, you use them at the end to delete dynamic memory. Perfect answer, right? Well, right. So the copy constructor and the operator equals overload. Remember, we could say something like our day, in fact, we had to in this homework 3, day list like I equals star new day. Right? When we say that, what does that actually mean? What's going on under the covers? This says whatever new day is pointing at, find that data and copy it into our day list at this position. So it's all about copying the data, right? Now, if new day has an event list in it, right, and that event list is made up of some array that has a pointer like event list, which is a pointer to the beginning of the array, the default copy constructor will only copy the pointer. And it will say, OK, this pointer is going to be in the day list now. All right, what did we say the type of, let's see, where was it? This one wasn't it. What did we say this automatic memory does? It goes away at the end of the function, right? So if the event list was pointing to something that's going to go away during the function, then later on, if you just copied the pointer, it would go into here and it would be wrong. Like it would not work later. OK, that's the big problem with it. It would not work. So we have to write a copy function that says, oh, I know there's an event list. I need to go and copy this one and then this one and this one and this one and this one into the proper place in this event list. You see the distinction there? Like the default copy constructor will only copy it's what we call a shallow copy. It will copy anything that's integers or strings or that sort of thing. But it won't copy into arrays. It doesn't know how to. It has no idea the compiler's not smart enough to say, oh, he created an event list, and that's got a whole number of it just doesn't know how to do that. You have to create that code. Does that make a little more sense? Yeah. Operator equals, well, this one's actually the operator equals one because you're using the equals on something that already exists. Copy constructor is very similar. It just would mean that this didn't exist yet, and you'd have to, you'd go day let's see. This isn't a good example, but day d equals new day or something, right? Or star new day. If you hadn't already created it yet, this means use the copy constructor to create this new day by copying all the pieces properly. That's the way it goes. Okay, question, Dylan?
And this is a feature of C++, right? This isn't inherent to coding.
It is a feature of C++. It's also a feature of some other languages that use pointers in particular to do these kind of copying things. Yeah, it's an object-oriented language feature, but you should kind of know the basic outline of this. And you should know when it's used. Like if you see something that it's going to have pointers in it, and it's going to be, setting it equal to some other event or something else that's going to go away, that's probably using the operator's equal overload. Okay. Yes, Allison.
Would another problem with copying just the pointer into the array is you would have a problem because the type of data is wrong?
Would you have a problem because the type of data is wrong? No, you would have a problem that this already has a pointer to an event list. And if you just copied the pointer itself, that whatever that was pointing to goes away. So let me draw it like this. Let's say that this one, here was your data, right? Some event data, right? I don't know, event 1, event 2, et cetera. This is the one for day list. This one you've just created, and let's say it has, I don't know, let's say it's empty because you just created it, right? There's no events in this. If you want to copy this one into here and you only copy the pointer from this one that was pointing here now would get pointed over to here. And that's not necessarily bad, but did we ever delete this one? All of a sudden, this has nothing pointed to it anymore, and now it's just hanging out there in memory, and it never gets deleted. That's a memory leak. So that's another problem with it. If you just copied it without the actual copy constructor, this one, like this statement, would only copy the pointer and would change the pointer pointing from something we want to something we don't want. That's the other issue. This would be a memory leak. It would not be a good situation.
But wouldn't the pointer for new day be pointing
It's
now to day list I?
No. This says take everything here and move it into here. So what it's saying is the event list pointer from here now points to this one, not the other way around.
Oh.
That's what it's saying. Okay? It's definitely subtle, and I'm not going to ask you to get into those subtleties necessarily. But you should be able to talk about the big idea. When you have dynamic memory, you need to create your own copy constructor so that all the memory gets copied in a deep fashion or such that it doesn't leave dangling memory and so forth. Yeah?
And that's what we had in homework 3.
It was in homework 3. I built them for you. I didn't make you do the copy constructors, but hopefully you looked at them. Or if you haven't looked at them, go look at them.
And that's when we went back from a certain point backwards and copied and moved things
Yeah.
around.
Yeah, that's when we moved all those things around. Yeah, good. Anybody else? Yeah, Dylan?
So what's the dereference operator on new day doing in this case?
OK. This dereference operator is saying, go into new day. New day has, I don't know, it's got an event count. It's got an event count. And it's got an event capacity. And it's got an event list, which is a pointer to some events. Right? OK, it's saying, OK, go into here. And with the default one, it's saying, copy this into the day list one, copy this into the day list one, copy this into the day list one. Right? And the pointer one's the problem, because this is just a pointer, and we want to copy all the stuff it's pointing to. And that's where you need to use your logic to figure, oh, I've got to do all that copying myself. Go look at the code. I actually you can rewrite the destructor to be, or the copy constructor to be a little better than the way I wrote it, but it works fine than the way I wrote it. OK? Question, Lydia?
Is there a difference between the operator equals overload and the is the
Yeah.
operator equal overload the copy construction?
No. That's a good question. How are they different? OK, the only thing you need to know about the difference is if you've already got something that's been declared and set up already. Like the day list was set up way at the beginning of your calendar function in our homework 3. If that's already been set up and you say equals some other thing, that's using the operator equals, because the point of the operator equals is saying, I don't need to create the new data structure. I don't need to create the new structure. The copy constructor would be this case where you haven't created a day list yet, and you're going to it's going to basically do the same thing. And if you go look at those two functions, they are very similar. There's just slight differences in them because of the fact that one is already created, one's not. The only difference. Okay? Don't overly stress about this stuff. There might be one question on it, right? Not going to go too much on there. Okay. All right. Let's look at static and dynamic arrays. OK, you guys need to know the differences between static and dynamic arrays. Like, why do we use one over the other? We already talked a lot about that, right? Static arrays, you've only got a certain size of the array, and you don't want to have to recompile your program every time to use like a larger amount of memory. Arrays have indexes, gives you great constant time lookup, right? You need to be able to say, what are good features about arrays? Why are they different than, say, using a linked list? Why are they better? You need to know how to expand the dynamic array, right? You should probably like go and review your code on how to expand a dynamic array, because you need to know there's 5 steps, and you don't want to miss any of those steps, right? When you do an expansion of a dynamic array. And we should think about the asymptotic behavior of dynamic arrays. Most of the functions are, well, if you know the index, the functions are just the constant time, O1. If you need to walk through the whole list, well, it's going to be ON. All right, things like that. OK? Questions on that? We've been doing a lot of that stuff. Here's a type of sample question. Write the insert at index function for some array. Right? You're given an index. Write the function that inserts the value at that index, and move all the values up 1, let's say. Okay, not a long function. I would not make you write the expand function in here. You might want to check for it, like if the capacity equals the count, then do the expand. But I wouldn't make you write the expand function for like this case, for instance. Okay, I'm not going to make you do 20 lines of code for a particular problem. 4 or 5 lines of code is probably about the max for an individual problem. Okay. Questions on that? All right, let's look at linked lists. So we've got a whole bunch of linked lists, right? We've got singly linked, well, 2. We've got singly linked lists and doubly linked lists. Linked lists are node-based objects. I already mentioned that it's not, they're not the only node-based objects we have, but they are kind of the first one we talked about. You should be able to know, I mean, you definitely need to know that you need to walk through lists to get to a particular value. You're really only going to keep the head or maybe the tail. You're not going to be able to keep individual pieces of it, like be individually addressable. Reason through a linked list operation with a picture. In other words, I might give you a picture of something like this doubly linked list, right? And I might say, delete this final node. What do you have to do with that? And I want you to draw a little picture for me and say, OK, well, let's see. If I'm deleting the final node, this one's going to go to null. And you might say that could be the first thing I do. Or you search through this, and you find out it's the one. And like the first step is going to be make that null. And then this one you can delete. I guess that's really about it for this one, right? There's not much else to do on that one. Probably wouldn't make it quite that easy. But point is, you have to be able to draw a little picture on that. OK? I don't think I'll make you write code about doing linked lists. Maybe, but not much. Might have to debug some linked list code. But that would be it. Deleting a node in a singly linked list. Remember, you can't do it if you just have the previous, or if you just have the node itself, right? If this was a singly linked list, right, and I want to delete that one and I'm given that one, problem, right? Problem is you can't point this one around it because you don't know where this one is. How would you find this one if you only knew this one? Susie? Yeah, you'd have to go back to the first one, and then walk through until this one's next equals the one you're looking for. Yeah, so it's kind of painful, right? That's why our delete for a linked list was generally give me the previous node, which was kind of ugly, but it works. It's the simplest way to do that. OK, all right. Let's look at some more stuff on linked lists. Doubly linked lists, remember they're forwards and backwards. It's more efficient because you only need the one node if you're deleting. I'm throwing this in here. Look, I know linked list operations can be tricky. How many people were here till like 2 in the morning on that homework 2 trying to debug that stupid linked list thing, right? It's a pain. Yeah, those things they're tricky to do, which is why I think drawing pictures is a little easier in the big picture. No pun intended, right? It's easier because you can describe it easier than coding it properly sometimes. And I'd rather you know the bigger picture than, and I want you to know how to code it, but that part you have to spend more time on. Okay. We also talked about circular linked lists a little bit, like the fact that at the end they have a pointer back to the beginning, right? And at the beginning they point back to the end, right? I might ask you a question on, say, what's the problem with, if you have a node, is there a way to search through the whole list if it's a circular list? Sure, you just keep walking through. How do you stop? Like I might say, well, what's the problem? Oh, stopping, you have to make sure you keep the one you started at, or you'll just keep going forever, right? Because there are no nulls in a circularly linked list. Things like that. Okay? Yes, Bobby.
When you say
Oops.
positive or negative, is it like, why is it a pro or con?
Yeah, what's the pros and cons to using doubly linked lists, for instance? Okay? I mean, not lots, but there are some pros and cons, right? You can walk backwards and forwards in a doubly linked list. It takes up more memory. It's harder to code, sort of thing. Okay. All right. Here's a sample code. Find errors in some linked list implementation of insert before. I might make it so that the pointer's in the wrong place, or it's not pointing to the right. This is where drawing a picture could be really important. Okay. All right. OK, then we talked about recursion, right? So recursion, as you know, is not it's not magic, right? But it's tricky, and it's not the easiest thing to necessarily understand. You need to know what they call themselves. You need to be able to write a simple recursive function. I'll give you one that's actually probably more advanced than the one that I might make you write in a second. All right? But there's lots of different examples of recursion. Okay? Maybe you want to think about why recursion is, how recursion is like stacks, maybe, or how recursion is, why recursion is sometimes slower than doing a non-recursive solution. Be able to discuss that sort of stuff. Okay? I'm seeing people write all this stuff down. It's online, remember. Slides are online. OK. All right. Here's the question. So write a recursive function to calculate the sum of the first even numbers. That one actually might be a little too advanced for like a test like this. Probably not. But let's try to do it. Hopefully you Comp 50 people will shine at this. You shine at everything, right? Of course you do. All right, let's try to write this. So think about this for a second, and think about how we would have to do this recursively. We're trying to sum the even numbers, the first n even numbers, right? So if I said int sum evens, right? Int n, right? What kinds of things are we going to have to do? How about this? Before you even tell me like what the code might be, what's a good way to maybe like think through the problem? Yeah.
Your case where you don't make any recursive calls first?
You do the non-recursive solution first. That's not a bad way to do it. If you wanted to write this as a non-recursive function, you could. Oh, you do 0 first. Yeah, sure. Let's do 0 first. So what happens if we're trying to find the first n integers and n is 0? What's the answer going to be? 0, right? So what are we going to say? If n, oops, thank you, equals 0, right? Then what are we going to do? Return 0, yeah. OK. And then that might be our base case. Sure. OK, so that's good. Now, the way I might think of this is well, what were you going to say? We're going to put our final return statement? Yeah. Maybe, but you mean there might be other return statements in the middle?
No, just one return.
Oh, there's just one return. What's it going to be?
I would say return 2n plus some evens n minus 2.
OK, very good. So you've solved it. That's great. Let's step back one step. No, that's terrific. If you can think that through, I'm like not very good at thinking that through, like kind of in my head. What I might do is say, all right, first of all, am I going to be counting up or down here? If I'm given the first, if I'm saying I need to count up to the first n integers, if I keep counting up, what's the problem going to be?
You don't have
there's nothing to stop at, and we're trying to stop at 0, right? So you're definitely going to be counting down, so very good. OK. And let's actually just write a couple of these out. That's what I might do. I might say, all right, I don't even know what, so let's say n was 0, 1, 2, 3. OK, what is the sum evens going to actually be? We already said it's 0 for 0. What is it going to be for the first the first even? What's going to be for the second even? Yeah, 6, because you're doing 2 plus 4, which is 6. And then how about 3? Yeah, you've got 2 plus 4 is 6 plus another 6, right? So it's 12, right? OK, and you could keep going on this. OK, now this is where you go, OK. So now we could write our little, now we could start thinking, OK, now we have to go down, down, down. Well, what did we deal with in this one? We dealt with the 6. That was the one that came out of this one. And the 4 came out of this one, and the 2 came out of that one, right? So now we can start thinking, OK, each one we're going to do, what did you say again?
Twice.
Yeah, return, right, 2 times n, right, which makes sense. OK, that would give us the 6. Then what?
And then you go to the next lowest value.
Which means what?
You can call sum even.
There you go. So what's it going to be? It's going to be plus sum even, because we're summing them, right? Sum evens, right? N minus 1, like that. And that should do it, right? And you can check it. And you can say, all right, for the first one, we're going to have, let's say it was n equal to 3, like we did up here. All right, if n equals 3, it's going to be 2 times 3, which is 6, plus the sum of evens of n equals 2, which was 4. So 6 plus 4, plus the sum of equals of n equals 1, which is 2, plus the 0th one, which is 0. And that equals 12, which is what our answer is. So good. I probably won't make you do that much like mental arithmetic, but it'll be something similar to that. And by the way, this is a 2-line recursive function, right? Not a hugely long amount of code. If you're writing more than a few lines in these recursive functions, stop. Right? You've probably done something incorrect mathematically. Question?
I just didn't understand all the math happening. It's like
Oh, you didn't get what was going on?
Yeah.
Does this make sense? 2 times the number plus the sum of the events n minus 1.
I get calling it within passing n minus 1. I don't get it 2 times n.
OK, so let's look again here. If we're counting the 0, we know it's 0. The answer is going to be 0. The first integer is 2, so we're going to just return 2. The second integer is 4. 2 plus 4. Where'd the 4 come from? It was 2 times whatever n was, which is,
The relationship between the n and the 2 and the 2.
yeah, and 3 and 6 and 2 and 4 and 1 and 2 and 0 and 0. Those are all times 2. Again, I probably wouldn't make you do this. That kind of thing is probably fair game for maybe the final one. We had a little more practice on this stuff, but something similar, but maybe not as hard to understand. OK? All right, that was recursive stuff. OK, question. What's the big O notation for this? Oh, this one's tricky. What is it? Why is it order n?
Because you have to make one recursive call per x times all.
Yeah, you have to make one recursive call up to the number or down from the number of n, right? So that means it's going to be order n, which, again, you've got to do all this. You've got to basically count calling a function as one operation. It might be 50, but it's going to be 50 times n instead of just n, which is still order n. Good. I won't make you go into any more detail than that. Yeah?
For any recursive function, the number of recursive calls, is it like n to the power of the number of recursive calls?
N to the number of recursive calls. Probably, yeah. Like the Fibonacci one was n squared, I guess. Or no, 2 to the n. Actually, not even n squared. I think it was 2 to the n. Yeah, so it's the number of recursive calls to the n, probably. Yeah, you don't want to do that in recursive functions, remember. Right? Fibonacci was bad because this whole expanding of the recursive calls, exponential function. OK, that's good enough for recursion. OK, we talked about stacks, right? Stacks are a simple data structure, and that's good because that means that when you have a simple data structure, you can probably get some benefits out of it. In other words, you can get behavior that's, say, constant behavior. How can we get constant behavior from a stack? There's only one place we can remove a value, the top of the stack. You need to be able to talk about details for stacks, for instance, of why they're order 1, right? I don't know, and why they are like useful for lots of things. I mean, there's lots of different uses for this. I might ask you to do a little write something that involves a stack, right? Pushing and popping onto a stack. You probably won't have to write the stack functions, although I guess I could ask you to do, write me out the pop function or something like that. Stacks, remember, are last in, first out, right? That was kind of a key portion of that. That's good for a lot of things. We can use it for postfix notation, converting infix to postfix, all that stuff. You probably won't have to go too much into detail here, although I might give you a tree and say, give me the postfix notation and show me how a stack might be used for that, something like that, right? I think that's fair game. Let's see, what else? You can't do it for level order, for instance. Oh no, I actually have more batteries this time. So let's see, what else on stacks? Well, for stacks, you're definitely going to have to explain how those functions are used, right? And you're going to have to explain how to use a stack, or you might have to explain how to do some of these traversals, right? I could say, I guess I could say, why can't you use a stack to do an in-order traversal? But that would be kind of mean. Not an in-order, sorry, a level order traversal. That would be kind of mean. But there we go. OK. Yes, question. You can use stacks with either arrays or linked lists, sure. And in fact, that's probably a fair question. Like, what's the benefit of using a stack with a linked list, for instance? You don't have to keep extra memory around. You don't need to expand any arrays or anything like that. So yeah. So there's no default type of storage for a linked list. And keep in mind, a lot of these data structures, like when you talk about the difference between what's the word? Like an abstract data structure, right? Or when you're talking about that, there are not necessarily default ways of doing it. You can use it with an array, or you can implement it with an array or a linked list. Or I don't think you could do a stack with a tree, for instance. But maybe if you could figure it out, you might be able to. Yeah. But yeah, you don't have to worry about, or you have to kind of separate the abstract data type from the implementation. Yeah, good question. All right. Queues. We talked about queues as well. We did a whole lab on queues, right? First in, first out behavior. Insert at the end, remove from the front, just like a regular queue, a human queue. Okay. Same as the stack. It's got some really primitive operations which are fast. Why are they fast? We know where the answer. We know where they are. We don't have to search through a list. Okay, we can define where those are. We don't need to move out with a queue. We don't need to actually move the elements when we delete from a queue, right? Remember how we walked through that queue up to the end? And that led us to what kind of queue, which made sense? An array, but what kind of an array? A circular array, right? Because you wanted to, you walked through and you circled back around when you got to when the front of the queue started walking to the, this way, right? And remember, one of the nice things about queues in general is you hope that you're inserting at about the same rate as you're removing from a queue. It's kind of the idea, so that you don't need to do all these expansions very often if you happen to be using an array. You don't have to expand it very often. Why? Because you're hopefully removing about the same number of things you're inserting in about the same rate. Okay. Let's see. You should probably be able to talk through a circular queue expansion. Remember, that got kind of ugly. We did it in lab, but it did get a little ugly. Go back and review the code for that from lab. And let's look at a sample question. Write the enqueue function for a circular queue. I would probably not make you write the expand for the circular queue. That got ugly. It took a while. It took an hour in lab, right? I wouldn't make you do that now. But I might say, you might have to say in there, expand now. If this is true, expand. But that's where we would leave it at, right? Remember, when a circular queue, if you're enqueuing, right, you are enqueuing at the back, and the back pointer moves. There's some point where it has to rotate to the front of the queue, or to the front of the array if you're doing it in an array, et cetera. Okay? All right. Might ask you to do that. Other questions on queues? Good. Then we talked a lot about trees. We started with trees that we started with some tree vocabulary. this might be a good idea to put on your study sheet. Like if you don't remember all the different vocabulary, what's the difference between length and depth, and what's the difference between a sibling and a grandparent or something? I don't know, right? I guess you probably wouldn't have to ask that. But but some of the vocab, put it on your sheet, and then you won't have to worry about it when asked questions that involve those. One of the things we talked about with trees, the first type of thing we said was you could have links to all of your children, but that becomes a problem when you don't know how many children you're going to have. You could make it a linked list, and that's not the end of the world, but that's a little slower. Or you could do this weird asymmetrical thing where you have first child and then next sibling. That was asymmetrical and kind of ugly, but it worked. Worked well for file systems. You wanted to do that. Trees are very good for recursive coding. Why? Because like other linked data structures, they are inherently recursive. You've got a node, and it's pointing to other nodes. That's a recursive definition, more than just recursive behavior. Okay? All right. There's a few slides on trees here. We had binary trees, right? Binary trees solved that horrible problem of having too many nodes and not knowing how many there were. We'll just leave it at 2. And then you've got cool data structures that come out of that. You've got binary search trees, right? Binary search trees you've got that ordering behavior in there. Okay? You can definitely degrade into linked list behavior with these. I've mentioned that lots of times, where if you just insert something bigger each time, it's going to make this horrible long linked list instead of a regular tree. If you even for binary search trees. Okay? You can degrade it into linked list behavior, which means figuring out the asymptotic behavior, you have to think about that. Oh, if this is just a binary search tree that isn't balanced, it could have order n searching. Right? Not so great. Probably not going to be that bad, but in general, but it could be. You can traverse trees lots of different ways. You should probably be able to write down the various traversals. Given a tree, if I said print it out in order, you should be able to do that. If you want extra help on that. By the way, I think I'm going to reschedule my office hours to tomorrow instead of Wednesday, so that what's the point of doing it after like the test? I'll do it tomorrow. And you can come by and we can take a look at those sorts of things. Just know the difference between those. Okay. Binary search trees, right? They have this cool invariant that says all nodes to the left are smaller, all nodes to the right are bigger. Nice. Okay, that's the invariant, and that's how we can insert relatively quickly, and you have an average depth of this log n, which is great. You need to know find min, find max, contains, insert. You need to know kind of the basic idea of those. I'm probably not going to make you write one of these. This is another one where you might need to draw me a picture. I'll say insert into this binary search tree, draw me the final tree, and show me the steps you use to do it. That might be fair game. Know what lazy deletion is. Why do we care about what is lazy deletion? Yeah?
Just marking it as being deleted.
Just marking it as being deleted. You might want to think about why we would do that, right? And we talked about lots of those, well, a couple of those reasons. We talked about if you know you're going to be inserting and deleting a lot, and you might insert things you've just deleted, well, don't bother deleting it. That takes too much time. Just mark it. Yeah. Do you have a question? Yeah.
For remove, when we went over it in class, we came up with a couple different ways in which we could do it.
Yep.
It doesn't matter which way we write on test as long as it's
How about this? Yes, it matters. Use the one that we talked about in class. That'll make grading easier, and you'll have to, that one's probably the best one anyway, in general. So go back to that slide, look at the way we removed it. Remember, it wasn't that hard, right? It was insert as you normally do, right? And then, remove the node and there's 3 cases, right? Case 1 was if it has no children. Case 2 is if it has 1 child, which is easy, relatively easy. And then case 3 was the hard one with 2 children. If it's 2 children, remember, go to the largest node, find max on the right side, and then put that one as the node, and then that will only have 1 child, so then you do the 1 child recursive deletion. So go back and look at it if that didn't make any sense to you. It's not that hard, just learn that one. Okay, good question. All right. OK. Here's an example question. Describe how to insert or delete from a search tree, right? Which is harder, why? Not too bad. Pictures are probably your friend in this. Okay. All right. We talked about AVL trees. You should be able to, as I said earlier, I'm not going to make you write code to do an AVL tree. But I might ask you to describe how you do rotation. I might ask you to do an insertion or a deletion or something from an AVL tree. Okay, and pictures again, probably pictures. Okay. What do we care about AVL trees? They're this compromised tree that's not perfectly balanced, because that's hard to do, but it's also not degraded into a linked list, so it's nice. You should know what, you should be able to describe what an AVL tree is and what it means to be an AVL tree. Okay. All right. We have to know about this rotation. Please go look at the notes on rotation of an AVL tree. You could put it on your cheat sheet. It doesn't really matter to me. Right? Let's see. Remember, there's a couple different cases. If you're left-left or left-left, then you only have to do one rotation. If you're a right-left or a left-right, you have to do a double rotation. At least know that when the cases are for those. AVL trees are coded with recursion in most cases, because it's easier to get it right, as it turns out. But they end up somewhat slow, and that's kind of the trade-off. But it doesn't really matter, because we're still talking, log n behavior, so it's all right. And I did tell you the dirty little secret about AVL trees is that they're not really used in real life too much, because, did I say why? Probably did. What do you remember why? There are other options, which are the similar idea, that do rotations slightly differently, that are harder to understand, but do it a little bit more optimized. Yeah, good. OK, questions on AVL trees? Types of things we might need to know for that? OK. Sample, well, there you go. How do you insert into an AVL tree? I might make you draw a picture of it, or I might make you describe what you'd have to do. Right? Insert as you would a binary search tree, then do a rotation based on the following things. 2 or 3 lines. OK. All right. We did talk briefly about representing trees as arrays. Right? Again, if you don't want to memorize these little mathematical arithmetic functions, write them on your sheet. Right? We talked about how if you do a complete binary tree in an array, it's actually really efficient. No links necessary. The links are embedded in the arithmetic. Right? No pointers. You've got non-complete trees we can represent. But that gets tricky, because all of a sudden you've got lots of space, and it might be a very sparse tree, and so you'll waste space that way. So there's trade-offs. Again, this class is a lot of times about trade-offs and why you pick one thing over another. Okay. Questions on that? All right. Of course, I'm going to ask you, this is one of the ones that can kind of go through any question on the test. Right? I could always say, tell me the asymptotic behavior of this function you just wrote. Right? Primitive operations are, again, I'm not going to care if you have a primitive operation that you call 1 or 2, because it's 1 or 2. Those constants are irrelevant to the big picture. Don't worry about that. You should be able to figure out that loops, for instance, go loop through. If you need to loop once through the list for all the variables, well, that's going to be order n. That sort of thing. If you're breaking a problem into 2 sections each, or into halves each time, that's order log n. That sort of analysis. You need to be able to think about that. Disregard constants. And we should be able to order those functions by their boundedness. If you have a number of functions, figure out what their big O notation is, and then order them correctly. Okay. Questions on that? I have a good example for you. Well, no, sorry. The important ones. We will not worry about O n log n yet. We actually haven't talked about any structures that's the behavior, so I'm not going to worry about that. The other ones, though, you should know about. Right? You definitely need to know that exponentials, bad. Heat death of the universe kind of thing, if you're going to be doing too many iterations. Quadratic. What's a good example of where quadratic equations are necessary? Nested for loops, sure. And remember where I said you see that fairly often? Monitors, yeah. Well, graphics, right? 2-dimensional graphics. The 2-dimensional part means you're going to be reading this way all the way down and this way. That's 2 dimensions. And therefore, you're going to have a nested loop to do that. Right? And if you have to do 3 dimensions, because you're trying to do the 3D world, it's cubic, which is even worse. So that's why we have companies like NVIDIA that design fancy, fast graphics cards to do some of this stuff. Okay. All right. So let's see. Here's some more hints. Oops. Order 1, constant, not dependent on the number of things in the data structure. Very nice. We like that because it can scale as big as we want it, and it doesn't matter. We'll still be able to get constant behavior. N, not terrible, but it means you can access all your, you do have to access all your elements, or at least in the worst case versus the best case. N squared, nested loops of n. Log n, this is where you break the problem into halves. Okay? Log base 2n. If you had log base 3n, you'd break it into threes. Susie.
For all these questions, will you specify when you want best and worst?
Yeah, I will specify when we want best or worst. Yeah, I will not ask you average ones, because that's more mathematically challenging than what we'd have in here. But I would say, hey, what's the worst case? But if I just ask what's the asymptotic notation, always think, oh, worst case, right? You could certainly say, hey, in best case it's this, worst case this. But if I just ask you flat out, it's definitely worst case. Okay? All right, good. Sample questions. This is kind of, again, it can go through. I'll ask you some specific ones about this, but pretty much any question is fair game where you could ask about that. Okay? All the ones we've discussed anyway. Okay. All right. We did talk about prefix trees, otherwise known as tries. Okay, this is the reason we mentioned this one was because A, it's actually used fairly often for English dictionaries, right? It's like it's a very good data structure when you have lists of words that have lots of similar prefixes or the same prefixes, right? Has great asymptotic behavior. Remember, when you're using a try, you do not need to go through the number of elements in the whole dictionary or the whole try. It's only your search is limited to the length of the word you're searching for. Very nice. Okay, very nice. For those of you who missed lab or missed class, you wouldn't know what this is all about. But Yoda, not a fan of tries. Okay. Let's see. Those are the big things on tries. I've got a couple pictures that we had from the last ones. So remember, tries look like this, where you have all the different nodes here. Oh no, this cannot be dying on me again. All the different nodes on here, and you have to talk about you might want to talk about, hey, what are the benefits of this? Well, lots of prefixes are, if lots of words share prefixes, it makes the tree relatively small. A trade-off is that you might have as many as 26 nodes or 26 children per node. Not so great. Trade-offs. Okay. One of the TAs I was talking with said that they hadn't talked about tries in her data structures class. She got this question, or a question about this on an interview she went to for like some company, right? And they said, in a compressed try, show us how you'd rearrange the try or how you'd remove something, right? And it was just a matter of drawing it on the board. She didn't have to write any code. She just had to draw this. And she said she figured it out, even though she'd never seen it before. It was kind of cool. But it definitely takes a little bit of thought to do that. These asterisks, remember, you have to mark when you end words. Okay, like back in this one. There is no word. If we were to look for the word fi, which might exist in English, but it doesn't exist in our dictionary yet, or our try yet, you would go fi. Oh, it's not marked as a word, so that's not in our dictionary. Whereas fish, you get to the h and it is. Okay. All right. Let's see. Sample question. Why is a try also called a prefix tree? Not a bad question, right? I mean, what's the deal? Well, the deal is prefixes are used. They're shared and they compress very nicely into the try. All right. Then finally, we talked about priority queues. And this was the last little thing we talked about before, or at the end of last lecture. Priority queues, you got to know that they rely on keys. And then the keys don't have to be unique. If you have two keys that are the same for two different elements, you don't get to decide which element you get back. If you ask for the min element, it can give you one or the other, or it can give you all of them, depending on how you implement it. Right? But you need to know that. If you wanted to differentiate between the two, you'd have to give them different keys, bottom line. And then the keys are stored with the elements. You need to know that. Okay? We talked about a couple different ways to implement priority queues. Right? We talked about, first of all, we talked about the different operations. Again, much like stacks and queues, very simple. That gives us lots of benefits. Right? It gives us benefits of being fast, gives the benefits of being able to code relatively easily. Chad M, who's in the other section, actually emailed me with a very good question about the priority queue code that I had messed up on, and I'll show you. Well, I'd kind of messed up on it, but I'll show you what it means. And I'm glad he emailed me about it because it made me go back and look at it and say, oh, this is something wrong here. Take a look at this. So this is what we had before for the remove min in the unordered priority queue. In the unordered priority queue, we had remove min, and remember I had this little helper function, min index, which said of the array, go through it and find the minimum index. For an unordered array, you have to walk through every value before you find the minimum, because it could be anyone, including the last one. So this is definitely order n, right? What about this statement? Sorry, it's a little hard to read. But what this is saying is, OK, once you know the minimum index, go through from that minimum index and move everybody back one. OK, so for instance, if this was our array, and I wanted to remove that one, what I said was move this one here and move this one here, and then you're fine, right? Turns out you don't actually need to do that. Any ideas why? Let everybody think about this for a sec. Why might we not want to, or not need to move everybody back one? We definitely need to fill this spot. We could mark it somehow, but we're not going to mark it. We need to fill the spot, but we don't need to move everybody back. What do you think? What do you think, Dylan? You had your hand up too, but what do you think?
Sure. So it's a priority queue, right? So we have these little keys attached to
Yeah.
our values.
Yes?
So the place in the array doesn't actually matter. So
Ah.
we just go all the way to the end, take what's there, and move it
Exactly.
inside the array store.
So what Dylan said, for those who didn't hear, is exactly right. In an unordered array, it doesn't matter what the order is. So therefore, to replace the value here, just grab the last one and move it here. You don't need to walk through this again. Now, this didn't change the behavior in the big O sense, because you've got a big O(n) here and also a big O(n) right next to it. They're not nested, so it's still big O. It's like 2 times n instead of just n. But we can write it much easier and just say, fine, grab the last one and stick it in the place where we're deleting, and that's the end of it. And make sure you lower your size. What is your question?
I was gonna say that does it change the asymptotic?
Oh yeah, it does not change the asymptotic behavior in the big picture, but it is twice as slow, right? And so when you think about it, you're like, oh, twice as slow. But remember, constants don't matter in the big picture. They would matter in your individual implementation in the sense that somebody else could say, I could speed it up by half. Yeah.
Is it twice as slow though?
Is it twice as slow? In the worst case, it's twice as slow, right? What if the minimum was the first element? You still have to go through all of them to find the minimum. That's one order n. And then in this one, you're saying move everybody back. So yeah, twice in that case. Not on average, but in the worst case it is. Okay. So anyway, so I screwed up. I'll have to go change that on the other slides. Okay. All right. Fixed. Yeah.
What is I then in that case?
So, it should be min index. You're right.
Oh.
Should be min index, yeah. Was it I on the last one too? Oh, no, you're right. So yeah.
The second one O(n)?
Why is the second one O(n)? How many elements did it go through?
But now if you already know what the index is.
Well, this one's not O(n).
Why is it like 2n?
This one is not. This one is just constant, because you have to do one operation. You have to move the one at the end here. So now this is constant. This one's still big. This one's still order n, because you needed to go through every element and find it. Yeah, so that was that. OK. All right, so we did talk about a couple different ways to do this in the unordered and in the ordered. And you should know the differences and why this is important, OK, or when you might use one over the other. It's all about your usage case, like what you're planning to use this for. OK. And we might see a better way to do it sometime later. And let's see. Sample question. Explain the functions of a priority queue. Those are the functions we talked about here. Insert, item, min element, remove min. And the trade-offs between using a sorted array and an unsorted array for a priority queue. Okay. And that's that. So Like I said, I'm going to go back to the office and put a little note on Piazza about my office hours tomorrow. It will probably be around this time tomorrow, so 4 p.m. or so tomorrow. If you have any other questions about preparing for the midterm, please email me. I think that should do it. All right, we'll see you guys in lab or on Wednesday.